Hello, in today's video we're going to be talking about the covalently bonded systems, unlike the last video where we were talking about ionically bonded systems. And then we will move into these polyatomic ions and see how they can be bonded and go back into an ionic bonded formula. So first off, let's talk about what a covalently bonded system is, and then we'll move on to how to name these things. Each of the namings that we've come across, each of the formulas that we've come across, has its own unique way of naming. So we saw on the previous video that ionic bonds between a main group metal and a nonmetal has one type of naming rules. Between a transition metal and a nonmetal has a different type of naming rules. And this is going to be our third type of naming rules. So covalently bonded systems have their completely different rules than either of those ionically bonded systems. So what is a covalently bonded system? Well, covalently bonded systems generally occur between two or more nonmetals. I say generally, we will come across a few cases where it's not two nonmetals, but for the most part, and especially in this class, we're going to be talking about covalently bonded systems between two nonmetals. So let's see how this works. Here, let's say we have two hydrogen atoms. If you remember your periodic table, the hydrogen is actually a nonmetal, and although it's over on the metal side of the periodic table, it acts as a nonmetal. So if we have two hydrogen atoms, each one has a proton and each one has an electron. As these move closer and closer together, something starts occurring. And so unlike the ionic bonds where one atom gives up an electron and the other one receives an electron, covalently bonded systems, there's this more of a sharing that goes on. So let's see what happens when these things move closer together. Well, as they move closer together, the proton of one atom, of one H atom, sees the electron of the other H atom and actually starts drawing it towards it. So up at the top, this is when they're far apart. You can see that they're spherical in nature, each of these atoms, but as they get closer and closer, they start getting deformed and they start looking more like an egg-shaped, an ellipsoid, if it were. And so this proton sees this electron, it starts pulling it towards it. This proton sees this electron and starts pulling it towards it as well. So both protons want more electrons because they're positive. Just in general, all protons are positive and all electrons are negative. So they're going to be drawing these negatively charged particles towards them. As you get closer and closer and closer, here, what happens is you actually get a bonding that occurs here. And what you can see is the color of all three of these plots. The lighter the color, the less dense the electrons are. So the electrons aren't really found there too often. The darker, the more dense the electrons. And so if we look at this side over here on the right, there's really a dark, dense electron cloud inside or in between these two protons. The fact that the electrons are actually in between these two protons make covalently bonded systems extremely strong. So unlike your ionically bonded systems, where I told you before could kind of just dissolve in water, covalently bonded systems are much stronger than ionically bonded systems. I can throw any covalently or almost any covalently bonded system into water and it'll still remain a covalently bonded system. It's really hard to rip these things apart. And that's because this proton is happy, it has all these electrons next to it. And this proton is happy because it has all these electrons next to it. So there's really like a dense soup of electrons in between these two protons. So this is the idea of what happens in a covalently bonded system. So let's talk about some naming. Molecules. You've heard me talk about compounds when I'm talking about ionically bonded systems, but covalently bonded systems are called molecules. And so that's why you've probably heard me say water molecule. I don't say a water compound, I say a water molecule because it's a covalently bonded system. So molecules are covalently bonded systems. Most covalently bonded substances consist of molecules. So it's kind of a both. If you have a molecule, you're a covalently bonded system. If you're a covalently bonded system, you're a molecule. That's different than your ions and your ionically bonded systems. Remember, in ionically bonded systems, one atom gives up an electron, the other one absorbs the electron. So unlike this giving and taking, covalently bonded systems share the electrons in between the different protons. There are no molecules when talking about ionically bonded systems. So this is like All squares are rectangles, but all rectangles are not squares. It's the same type of thing. All molecules are compounds, but not all compounds are molecules. So only ionically bonded systems are compounds, they're not molecules. So that's just a kind of a fine point, and you'll kind of probably hear me interchange the two during lecture. A lot of chemists get really relaxed in the way that they use interchange molecule and compound, but really compounds are ionically bonded systems, molecules are covalently bonded systems. So let's start actually naming these things. Just like we did with the ionically bonded systems, we're going to first talk about the binary covalently bonded systems. What that means is we're going to take two different elements and we're going to have them interact with each other in this covalently bonded system. Unlike the ions, where we don't change the name of the cation and we modify the name of the anion, there is no cation or anion present in a covalently bonded system. And so what we do is we use prefixes in order to denote how many of each element is present in this molecule. So this is how the general formula for writing this covalently bonded molecule would look. We would have a prefix in the first element, and then we would name the prefix plus the second element, where we change the ending of the second element and add "ide." Now, how in the world do we know which element we're going to be writing first? Because in the ionically bonded system, the cation is always written first. So how do we know which element is element 1 and which element is element 2 in the covalently bonded system? Well, we have very specific rules. There's a lot of rules in chemistry, and this is one of the kind of unique ones. If you are dealing with a binary covalent compound, covalent molecule, the element with the lower group number is written first. So if we were looking between carbon and oxygen, carbon is group number 4, oxygen is group number 6. So carbon clearly has a lower group number than oxygen. Carbon is written first. That's why we can write carbon monoxide and the carbon is written first. What happens if both elements have the same group number? So like oxygen and sulfur. How do we know which one is written first? Well, if that happens, if both elements have the same group number, oxygen is group 6, sulfur is group 6, then the one with the highest period number gets written first. So oxygen is in period 2, sulfur is in period 3, so the sulfur would be written first. And this is why you see sulfur dioxide or sulfur trioxide with the sulfur written first. They both have the same group number, but then you go to the secondary rule, which is whichever one has the higher period number. And since sulfur in that case had the higher period number, it would be written first. So then the secondary element, we drop the ending of it and we add "ide." It's very similar to that ionic compound where you modify the ending. You're going to modify the ending of this. In this case, we do use the prefixes and we do drop off the ending of the second element. So let's do a few examples. Let's do an example and see how this is different than the ionically bonded systems and actually what those prefixes are. So here are your prefixes. I won't be giving you these prefixes on an exam or a quiz. These are something that you're going to have to know and memorize. So for the number 1, we write mono. That's pretty easy. 2 is di, 3 is tri. Great. Those are prefixes that you probably are used to already. The one that's really difficult for students to remember is 4. It is not quad like it is in a lot of other fields. In chemistry, it's called tetra. So you might be able to think about this because the video game Tetris, each of the blocks are 4 different blocks. So the long one has 4 different squares in it. The square one has 4 different squares. Each thing in Tetris has 4 different squares for each of the blocks. And so if you want to remember the number 4, just remember Tetris and it's tetra. 5 is penta, 6 hexa, and so on. You should familiarize yourself with all 1 through 10. We will be using all 1 through 10 when we're naming. So let's get to a compound. Let's see how we can modify or how we can actually write out the formula, how we can write out the name based on the formula. And then, of course, tomorrow in class, we will be going in the reverse direction where I give you the formula and then you write out the name. So we go in the forward direction today, and then tomorrow in class, we go in the reverse direction. A note, and I'm glad I put this on here, if the first element that is written in the molecule has a 1, a subscript of a 1, we would generally write mono, but if it's the first element, we drop off the mono. And so we'll see this on the next slide, the next example. And that's what we have here, carbon monoxide. Technically, it should be monocarbon monoxide. However, again, chemists are lazy. We don't want to have to write out things over and over and over again. So if the first element has a 1 subscript, as it does here, we don't use the term mono, we just drop it off. So this becomes carbon monoxide. So let's see a covalently bonded system between carbon and oxygen. Not that carbon monoxide that was on the previous one, but the other famous carbon and oxygen system. So we're going to use those Latin prefixes, and we're going to denote exactly how many elements are present from their subscripts using those Latin prefixes. So here, the name of the first element doesn't change. So just like the cation doesn't change, you don't change the name, you don't change the name on the first element written in the covalently bonded systems as well. Let's look at this CO2. Now you probably already know what the name is of CO2, but let's see how these rules are applied. We don't change the name of the first element. And how did we even know carbon was the first element? Well, we could check out their group numbers. The group number of oxygen is 6. The group number of carbon is 4. So carbon has to be written first because it has a lower group number. Great. So we don't change the name of the first one. And in this case, since there's a subscript of a 1 here, we should technically write monocarbon, but since it's the first element written, we drop off the mono. There's 1 carbon, we don't use the mono, so this is just carbon. Now for the second element here, we have 2 oxygens. And so we're going to have to denote this 2 using those Latin prefixes. So 2 in the Latin prefixes is going to be di. And we're going to drop off the ending of the oxygen. We're going to only take the first two letters of oxygen, OX, and add the I to it, just like we did in the ionically bonded system. There are 2 oxygens, so we use di, and then we drop off the ending, so now it's going to be dioxide. So this blue is your prefix, the red is your modified ending, and the black is the original letters that come from the element. So now, in order to put this all together, all we do is read the first one and the second one. So this would be carbon dioxide. You can see the same thing if it was SO3. Now, S is written first because it has the higher period number. They both have the same group number but higher period number. And that would be read as sulfur trioxide. So we'll go through a whole bunch of examples of this tomorrow in class. I just wanted to show you how the rules are applied. If the first element has a subscript other than 1, you do have to put the Latin prefix. So if this was C2O2, this would be dicarbon dioxide. But since this is only 1, you drop off the mono. So we'll be talking a lot about those examples tomorrow in class. Let's talk about, so that's all I want to name of these covalently bonded systems. Very easy. The Latin prefix, the lowest group number or highest period number gets written first, and you change the ending of the secondary element. That is the easiest naming that we will come across all semester long. Now let's talk about some polyatomic ions. So switching gears now, we're no longer in the covalently bonded system. We're moving back into this ionically bonded system. Here we're going to be talking about multiple elements bonding together in this ionically bonded system. So polyatomic, let's see how those are. This would be your carbonate ion. If you notice here, this is actually calcium carbonate. That's what's in chalk. Here we have a calcium, which is a 2+, and the carbonate ion. Now, unlike previously where we were talking about binary ionic compounds, here this carbonate already has 2 elements present, and this calcium adds 3. So now we have 3 different elements present in this ionically bonded system. So how do we name something like this? Well, I get a lot of students coming into me Dr. Beck, why can't we just memorize things? Here's your chance. The ones that are written in red are the ones that I want you to be familiar with, and I want you to know the name as well as the formula for each of these ions, including the charge. So ammonium, hydroxide, chlorate, nitrate, carbonate, phosphate, and sulfate. We will be using some of the other ones, but I will never quiz you or put them on an exam. I will only quiz or put on the exam the ones written in red. So those are the ones that you should memorize. So now we can treat these as a different type of ion. So much like the lithium element takes an Li plus, lithium plus 1, the ammonium takes a plus 1 charge as well. So when we're dealing with ionically bonded systems, we can just take the entire polyatomic ion and mix it together in this compound. So let's see how that works. So this table we're going to have to memorize, and we're going to be using these regularly. A lot of chemicals come from the hydroxide. Those are going to be our bases. These nitrates, those are salts. We deal with them a lot. Carbonate shows up quite a bit. Sulfate and phosphate, all of these show up, the ones in red show up a lot just in everyday life in chemistry. So how do we name a compound between an element and a polyatomic ion? This is easy. The way we do it is we take the name of the element, most likely it's going to be a cation, a main group metal, and we keep it the same. We keep the same rules that we did for both of the ionically bonded systems, binary bonded system. If it's a main group metal, you know what the charge is based on the group number. If it's a transition metal, you're going to have to use Roman numerals in order to name it. That's fine. The name of the polyatomic ion never changes. So carbonate will always be carbonate. It will never be carbonide. You'll never drop off the ending. It's always just carbonate. So those are very easy to name. Anion's name stays the same. So we're not changing any of the names at all when we're talking about polyatomic ions. So let's see this one. We know calcium has a 2+ in this case because it's a group 2 metal. Carbonate has a 2- because eventually you're going to have memorized that table. So this is the formula for calcium carbonate. How in the world did I name that? Well, we have a calcium is our cation. We don't change the name of the cations. The carbonate is our anion, but we don't change the name of polyatomics. It stays the same. So in order to write the name of a polyatomic ion bound in a compound, we just take the name of the cation, the name of the polyatomic anion, and we say it. So this is just going to be calcium carbonate. We don't change it. We don't use prefixes. The only time that this would change at all is if our cation was a transition metal. And then we would have to put our Roman numeral in there, just like we do with the traditional ionic compounds. That's it for naming for these compounds. There's nothing else I want to talk about in this video, but I do want to stress that you should memorize that those polyatomics. Hopefully by class tomorrow, there's only 7 of them, but we will be using these a lot for the remainder of the semester. So in this video, we talked about covalently bonded systems. That's where we use the prefixes. We've also talked about polyatomics. This is where we do not change the name of the polyatomic, and we don't change the name of either the cation or the polyatomic anion. It's just read the way that it's written, so calcium carbonate. Unless it's a transition metal when we do use the Roman numeral. So we'll be talking a lot about these tomorrow. I just wanted to give you a quick introduction to what these are. And with that, I want to end the video. Have a good night, and I will see you all